So what we're going to do, right, so these are two different things, right? But m is bigger than n, and m is less than k. So when we subtract n, what do we get? We get 0 less than or equal to m minus n is still less than k. And all these are integers. And what was one of the first things we proved, oh, sorry, they're all natural numbers, better yet. What was one of the first things that we proved about natural numbers and the relationship between, the order relation between division? If you got two numbers, and this one, they're both natural numbers, this one divides this one, what's the order relation between them? The one that divides is smaller. Okay, but this isn't here, so it's impossible for k to divide m minus n. That's the sentence I left out of the thing in the text, so it obviously is going to be confusing if you get to that point. Okay, but by a previous lemma, since m minus n is less than k, k cannot divide it. Unless what? M minus n equals 0, which means that m equals n. Okay, so the summary of this is that zk looks like this, and each of these are different, right? These are all unique elements in there, unique and different elements. Okay, so everybody pretty much got the idea here. Okay, let's do some calculations. Okay, so let's look at Z5. That's equal to 0 bar, 1 bar, 2 bar, 3 bar, 4 bar. Okay? And now the most basic thing you can do is figure out what something is. For example, what's 9 bar? It's got to be equivalent to something in there. So remember your division algorithm. 4 bar, right? Because the largest multiple of 5, less than that, is 5. The remainder is 4. Okay? So what about 28 bar? 3 bar. See, 5 is an easy one because everybody can figure out what the multiple of 5 less than it is, right? It gets more complicated if you're looking at, like Z mod 37. Okay, so everybody get the idea? Right? Because here, 9 equals 5 plus 4, that's my remainder. 28 equals 25 plus 3, that's my remainder. Okay? And so on. So now, if I, 1008 bar is 3 bar. Okay? So Z mod 5 is an easy one to work with. All right, now what I would like to do is add and multiply these things. Okay? Now, so let's try an example here. Let's try 3 bar plus 4 bar. Now, if you were going to do things in the way that you would want to do them, and sometimes things do work out in math the way you want them to, what would you say that's equal to?
7 bar.
7 bar. But we want to stay inside this collection here, and 7 bar is equal to something in there, which is what? 2 bar. Right? Because 7 is 5 plus 2. We'd also like to be able to multiply. And what should that be? 12 bar, which is also 2 bar. So 3 plus 4 is equal to 3 times 4. Okay? And the question is this legit? And the reason why we have to be careful is that if we look at this one, for example, 3 bar is equal to 8 bar, right? And so 8 bar plus 4 bar should also be equal to 2 bar, but actually it's 12 bar, but you know that 12 bar is 2 bar. But do you understand the problem here? That is, I have to be a little careful because these things have different, right? I'm sort of using these particular numbers here. And I have to be a little careful because what if I picked up a different number in this equivalence class? If I'm going to define it this way, I should get the same sum, right? It shouldn't depend on which one I pick up. So the fact that I picked 8 in this equivalence class instead of 3 should not change my sum. If this is going to be a legitimate, and the real word, mathematical term, is well-defined operation. It shouldn't depend on which one I pick. I'm basically adding sets here, right? These things are sets, and you're immediately stopping to think of them as sets, which is okay, but they are sets. And this, what I wrote down, depends on the choice of the set. Okay, so we need to check. We're going to define m bar plus n bar equal m plus n bar. That's really what we were doing over here, right? And so we need to check, and by the way, you're going to be checking multiplication as well defined, so you better pay attention to the addition one, right? Okay, need to check that, check the operation is well defined. You will see this all the time in mathematics when you're defining a function that involves choosing something. You have to make sure that your function doesn't depend on the choice. So this word will show up over and over again. Okay, so what does that mean? Let's suppose that m is equivalent, well, let's just put it this way, m bar equals a bar and n bar equals b bar. We need to show that a plus b bar equals m plus n bar. Does everybody understand what the problem is? Remember over here, I swapped out 3 and 8. And I checked in this particular case that, yeah, we still get 2 bar. What this does is say, whatever k you're talking about, this is always fine. That is, it doesn't matter what number I have under here. And you see, you're going to need that because even though here, you get kicked out to 12, and you want to be able to add 12 bar and 16 bar too, right? So you're going to need this. It needs to be checked that this is well defined. Okay, and it's actually not hard, okay? Because all we're doing is checking this, which means we're checking that the difference is divisible by k. All right, so let's do that. Okay, I'm going to use these two things here. And those mean the following. So we have that m minus a equals k r, where r is an element of z. And n minus b equals k s, where s is an element of z. And what is it we want to show? We're trying to show these two are equivalent. So what is it we're going to show then? Well, this, it will involve r and s in some way, but we want to show this bar equals that bar, which means their difference is divisible by k. A plus b minus m plus n is divisible by k. So equals, again, equals k times some question mark, where question mark is an element of z. So the strategy is basically just like what we did before, right? So a plus b minus m plus n. What's that equal to? That's a plus b minus m minus n. And then what happens when we rearrange? We get a, okay, so let me do it the other way. It's just symmetric, right? And I want to get my minus signs to work out. M minus m plus n minus a plus b. Sorry about that. I mean, it would work the other way, but then I get minus signs. Let's be simple. Okay, I'm doing that so I can match what I have up here. So m plus n minus a plus b equals m minus a plus m minus b equals kr plus ks equals k times r plus s, where r plus s is an element of z. So we've just shown that a plus b bar equals m plus n bar. Okay, sorry we're running just a little bit out of time here. I just wanted to check a couple things with z. So, and you'll check that multiplication is well defined also. That's one of your exercises. And so what I want to check here very quickly is that z mod 5, z5 is a field. So we're not going to check all the actions, but the only thing that it turns out that is missing in making something a field is multiplicative inverses. So let's check, and you'll have to do homework on z3, so it'll be even easier, that z5, that every element of z5 has a multiplicative inverse. Except, of course, which one? 0 bar. Because you see 0 acts as 0 by our definition, right? If we add it to anything, we get the same thing back. And 1 bar is our 1. And so really, the only thing that's missing, I mean, you can check all the associative law and all those things too, and that all works out. The only thing we're missing are the multiplicative inverses. So, of course, what is 1 bar inverse? 1 bar, right? What about 2 bar inverse? So we need something in here which when we multiply it by 2, we get 1 bar. So you can just go through and check what's 2 times 3. 6 bar, which is 1 bar. Done. Okay? So that equals 3 bar. Okay? So these are inverses of each other. So now we have to do 4 bar inverse. What's that going to be? Yeah, it's its own multiplicative inverse. And we're done. So Z5 is a field. And in fact, it's a very interesting fact. So ZK is a field if and only if, anybody care to guess? Actually, Z2 is a field. So it's not the fact that it's odd, right? Because you have 0 and 1. It's the smallest field in the world, right? 0 and 1, nothing else. Z3 is a field. Z4 is not a field. Z5 is a field. Z6 is not a field.
If it's
K is prime. So if K happens to be a prime number, you always get a multiplicative inverse. Now think for a little bit how in the world you might prove that, okay? It's really not very easy. But it is in the section that we're not covering on finite sets. And I'll talk about that a little bit more. Okay, so in about 3 minutes, there's going to be a fire alarm, but maybe you'll be out of the building by then, and then you don't have to actually